Okay, I hope I'm audible to all students who are attending this lecture of Mathematical Methods for Economics, Part 2. We intend to start with a new topic within our MME course. This is differential equations. Okay, and the book I prefer to follow for my lectures on differential equations. This is chapter 21 of the book Sydsaeter and Hammond. The fourth edition of this book. Okay, so let's start with our lectures on differential equations. So let's first understand what is meant by a differential equation. So a differential equation is an equation in which the unknown variable is a function often of time, which we denote by t, and the equation includes one or more derivatives of the function. The equation includes one or more derivatives of the function. Okay, so when we talk about a differential equation, it is that equation in which the unknown variable is usually a function of time, and the differential equation also includes one or more derivatives of the function. Okay, so now let's look at what is meant by an ordinary differential equation. So an ordinary differential equation is the one for which the unknown is a function. The unknown is a function of only one variable. So we can write, for example, dx by dt is a function of x and t, where x itself is a function of t, is the unknown variable. X itself being a function of t is the unknown variable. Okay, so clearly you can see that this is a typical differential equation. What is the unknown variable? The unknown variable is x. X itself is a function of time. And you can see that the equation includes one or more derivatives of the function. You can clearly see that this differential equation includes the first order derivative of x with respect to time, dx by dt. And usually dx by dt, we denote it as x dot. X dot means dx by dt. So I'm quickly revising till here. We have started our discussion on differential equations. When we talk about differential equation, it is that equation which consists of an unknown variable, which itself is a function of time. And a differential equation also includes one or more derivatives of the function. When we talk about an ordinary differential equation, in case of an ordinary differential equation, the unknown is only a function of one variable, not more than one variable. So clearly you can see on your screen, when I talk about the differential equation dx by dt equals f as a function of x and t, you can clearly see that x itself is a function of only one variable, which is time. Okay, and clearly you can see on your screen that the differential equation automatically includes the derivative of x with respect to t, which is denoted by x dot. Okay, now let's understand what is meant by partial differential equation. Okay, partial differential equation. So partial differential equation is the one for which the unknown is a function. The unknown is a function of two or more variables. In case of an ordinary differential equation, the unknown, which was x, was a function of only one variable, which was time. In partial differential equation, the unknown, which is x, will be a function of two or more variables. And one or more of the partial derivatives are included. One or more of the partial derivatives are included. That means the partial differential equation is going to consist of one or more of the partial derivatives. You can have more than one partial derivative in partial differential equation. Okay. Now in our MME2 course, we will be focusing only on first order differential equations. Partial differential equations are not a part of our MME2 course. Okay. So we will be discussing first order differential equation. So let's start with the simplest type of a differential equation. So we can write the simplest type of differential equation. The simplest type of a differential equation is x dot being a function of t, where all of us know that t denotes time and x dot is nothing but dx by dt. X dot is nothing but dx by dt. So this is the simplest type of a differential equation. You can clearly see that in this particular case, time is the only variable and x dot denotes the derivative of x with respect to time. Now, if we have to find the solution to this differential equation, then that involves integration. So if I have to solve this equation, I can write x dot as dx by dt equals f as a function of t, which implies dx is equal to f as a function of t times dt. Now, if I integrate both sides of the above equation to get the solution for this differential equation, integrating both sides of the above equation, I can write integral dx is equal to integral f of t dt. Along with that, we get the constant of integration. Now, integral of dx I can write as x. When you're integrating with respect to dx, you get x. This is nothing but integral of f of t dt plus. So I can write this is the solution of the differential equation x dot as a function of time, where c is an arbitrary constant. Where c is an arbitrary constant. Okay, so I hope all students attending this lecture have understood the simplest type of differential equation. X dot as a function of t is the simplest type of a differential equation, where x dot itself is dx by dt, derivative of the unknown variable with respect to time. If I have to find the solution of this differential equation, I can write dx by dt as a function of t like this. Dx is equal to f of t times dt. I can integrate both sides of the above equation. This is what we get. After integrating, we get x as integral f of t dt plus c, where c is an arbitrary constant of integration. And this gives us the solution of the simplest type of differential equation. Now, let us actually look at first order differential equation. So, we can now write a first order differential equation. A first order differential equation is written as x dot being a function of t and x, where f is a given function, where x is a given function of two variables, and x as a function of t is the unknown function. Okay, so what you can see on your screens is actually the first order differential equation, where all of us know that x dot is nothing but dx by dt. So clearly all students can see that the first order differential equation is a function of two variables, time and x itself is a function of time. That means x dot, which is dx by dt, is a function of t and x itself is a function of t. Okay, then we can quickly write a note. A differentiable function, x, which is itself a function of t, that is defined in an open interval I of the real line and satisfies x dot as a function of t and x for all t lying in the interval I, is called the solution of, it is called the solution of the differential equation in I. It is called the solution of the differential equation in I, and the graph of any solution is called an integral curve. Graph of any solution to the first order differential equation is called the integral curve. So let me quickly revise the note with all students. All of us know that this is the first order differential equation, x dot as a function of t and x. Now x as a function of t, which is defined in an open interval I of the real line, and that x as a function of t which satisfies my first order differential equation is called the solution of the differential equation. So basically I can say that x as a function of t is the solution of the first order differential equation x dot as a function of t and x, and the graph of x equal to x of t is called the integral curve. X as a function of t is the solution of the given differential equation, and when you plot the graph of x as a function of t, you get the integral curve. Okay, so now when we practice more questions, the concept becomes crystal clear. So let's practice a few questions based on first order differential equations. So let's look at these practice questions. Question 1. consider the differential equation. Consider the differential equation x dot is equal to x plus t. Part 1 asks us show that x equals minus t minus 1 and x equals e to the power t minus t minus 1 are two particular solutions. Show that they are two particular solutions of the equation over the entire real life. Okay, then part B asks us more generally, show that x, which is equal to c e to the power t minus t minus 1, is a solution of, let me call this as equation star. It is the solution of star for all values of t, whatever the choice of the constant c. And part C asks us show that x, which is equal to e to the power t minus 1, is not a solution of the differential equation star. Okay, so let's quickly solve this question. We are given the differential equation. You can clearly see it's a first order differential equation because you have x, you have t, x itself is a function of t. Okay, x itself is a function of t, and you have the first order derivative dx by dt. So it's a first order differential equation. Now let's solve part A. Show that x equal to minus t minus 1 and x equal to e to the power t minus t minus 1 are two particular solutions of the above differential equation. So first of all, let's consider x dot equal to x plus t, and we are given that x is equal to minus t minus 1. So let's verify whether x dot is equal to x plus t for x equal to this. So let's look at the left hand side. Left hand side is x dot. X dot is nothing but dx by dt. If I differentiate this, if I find out dx by dt, it's minus 1. X is equal to minus t minus 1. So if I find out dx by dt, that's minus 1. My right hand side is x plus t. What is x? X itself is nothing but minus t minus 1 plus t. Minus t and plus t cancel, we get minus 1. LHS is equal to RHS for all values of t. Okay, clearly all students can see that LHS is equal to RHS for all values of t. So I can say that therefore x equal to minus t minus 1 is the solution of the differential equation x dot equal to x plus t. X equal to minus t minus 1 is the solution of this particular differential equation. Okay, now erasing it off, let's look at the second case. Everything else remains the same, guys. The only difference is now my x has changed. So we are still solving part A. Okay, you can see part A. Now we have x is given to us as e to the power t minus t minus 1. Again, I can calculate left hand side, which is x dot, which is nothing but dx by dt. From this expression, if I find out dx by dt, it's e to the power t minus 1. Our right hand side is going to be x plus t. What is x? E to the power t minus 1 plus t. Minus t and plus t cancel, we get e to the power t minus 1. So since LHS is equal to RHS, Therefore, we can say that x equal to e to the power t minus 1 is the solution of the differential equation x dot equal to x plus t. So both of these are particular solutions of the equation over the entire real line for all values of t. Okay, now let's look at the B part. So I am erasing part A now. Let's look at part B. Now part A was telling us that we had to show that x equal to minus t minus 1 and x equal to e to the power t minus 1 are particular solutions. Part B looks at the general solution. So more generally show that x equal to c e to the power t minus 1 is a solution of the differential equation. So I am writing the differential equation given to us and I am writing the general solution given to us. Now we need to verify that this is a general solution of this differential equation, okay, for all values of the constant c. C is a constant, okay. So again, in order to verify, I start with the left hand side, x dot, which is dx by dt. If I differentiate this with respect to t, what do I get? C e to the power t minus 1. And my RHS will be x plus t. X plus t will be, what is x? C e to the power t minus 1 plus t. Minus t and plus t cancel. Again, we get c e to the power t minus 1. So since LHS is equal to RHS, we have verified. So I can say that therefore x equal to c e to the power t minus 1 is the solution of the differential equation x dot equal to x plus t for all values of t. Okay, so hoping all students have understood this part B. Now let's look at part C. Remember, when the question is asking you to show, you have to verify it. Basically, you have to show that LHS is equal to RHS. Okay, so erasing this off, let's now look at part C. Show that x equal to e to the power t minus 1 is not a solution of equation star. So again, we write equation star, which is my differential equation. And then I write x is equal to e to the power t minus 1. Okay, so again, let's verify. LHS is x dot, which is equal to dx by dt, which is nothing but e to the power t. RHS is x plus t, which is e to the power t minus 1 plus t. Clearly, what we learn, LHS is not equal to RHS. Okay, and we can write that LHS will be equal to RHS only when t is equal to 1. You can see that this will be equal to this only when t is equal to 1. But in general, for any other value of t except 1, LHS is not equal to RHS. So I can say that therefore x equal to e to the power t minus 1 is not a solution of the differential equation x dot equal to x plus t on any open interval. So I hope all students have understood question 1, where we have solved parts A, B, and C. Basically, we had to verify. We were given the differential equation. We were given the function x. We had to verify whether x as a function of t is a solution of the differential equation. We pick up the differential equation. We solve the LHS. We solve the RHS. If they come out as equal, we can say that x as a function of t is a solution of the given differential equation. Okay, let's now solve question 2. Find the solution of x dot equal to x plus t that passes through the point t comma x equal to 0 comma 1. Okay, so we need to find the solution of x dot equal to x plus t that passes through the given point. Okay, so now from question number 1 only we saw what is the general solution of the given differential equation. Same differential equation was there in question number 1 also, and we had seen that the general solution of the differential equation x dot equal to x plus t is x as a function of t equals c e to the power t minus 1. Okay, this is the general solution of the given differential equation. Okay, now we are given that it passes through the point t comma x equal to 0 comma 1. Okay, so we can say if the above equation passes through, if the above equation passes through 0 comma 1, then I can write x as a function of, so this is my t and this is my x. My t is 0, x is 1. So x of 0 will be c e to the power 0 minus 0 minus 1. So this will be c into e to the power 0 is 1 minus 0 minus 1, which is c minus 1. And what is x as a function of 0? It's equal to 1. This is equal to 1. Because when t takes the value 0, x takes the value 1. So x of 0 itself is equal to 1. So I can write c minus 1 is equal to 1, which implies c is how much? It's nothing but 2. C comes out as 2. So therefore I can say the required solution of x dot equal to x plus t that passes through t comma x equal to 0 comma 1 is given by x of t equals, this was the general solution guys, but what is c? C has come out as 2, so I can write 2 e to the power t minus 1. This is the, I can say this is the particular solution. Okay, so hoping all students have understood this particular question. So I'm again revising it. We had to find the solution of the differential equation x dot equal to x plus t that specifically passes through the point t comma x equal to 0 comma 1. So first of all, from question number 1, we learned that the general solution of this particular differential equation is this. It passes through 0 comma 1, so 0 comma 1 must satisfy this equation. Okay, so x of 0 itself is 1, and if you calculate x of 0, it comes out as c minus 1. So c minus 1 is equal to 1, which implies c is 2. You plug back c equal to 2 in the general solution, you get the particular solution. This is nothing but the particular solution of the given differential equation. It is nothing but the particular solution of the given differential equation. Okay, so let's now write a note before we move forward. Okay, so clearly you can see that in the above question, or I can say in the previous question, x dot itself was a function of t, which I can write as x as a function of t plus t. Remember, my differential equation in the previous question was x dot equal to x plus t. Now x dot itself is a function of t and x also is a function of t. and we were given that x as a function of 0 is equal to 1. Okay, so if t is equal to 0, denotes the initial time. If t equal to 0 denotes the initial time, then x of 0 equal to 1 is called the initial condition. It's just a point to note from the previous question. X of 0 equal to 1 is called the initial condition, and the problem is called the initial value problem. The problem is called the initial value problem. Okay, so I am again revising the note with all students. In the previous question, we had the differential equation x dot, which itself is a function of t, equals x as a function of t plus t. And in the previous question, all of you can recall that we were given t comma x equal to 0 comma 1. That means x as a function of 0 is 1. Now t equal to 0 denotes the initial time period, and x of 0 equal to 1 is called the initial condition. The problem which we had done in the previous question is called the initial value problem. It's just an important point to note. Okay, let's now practice a few questions from Sydsaeter and Hammond book based on first order differential equations. Okay, so let's practice a few questions. So basically this is going to be problems section 21.1 of the book Sydsaeter and Hammond. 21.1, let me correct myself. Practice questions from problems section 21.1 of the book Sydsaeter and Hammond. Okay, so let's practice a few questions. Show that x as a function of t, which is equal to c e to the power minus t plus half e to the power t, is a solution of the equation x dot t plus x as a function of t equals e to the power t for all values of c. Okay, so guys, we are given the differential equation. What is the differential equation? X dot t plus x as a function of t equal to e to the power t, and we are given the solution. We need to verify. Okay, we need to verify. So again, let's start with the left hand side. Left hand side is nothing but x dot t plus x as a function of t. This is my LHS. I need to show it to be equal to RHS, which is e to the power t. Now, what is x dot t? It's nothing but dx by dt. So from this, can I quickly find out dx by dt? It's c e to the power minus t times minus 1. Okay, plus half e to the power t. So my dx by dt comes out as minus c e to the power minus t plus half e to the power t. This is my x dot t. Minus c e to the power minus t plus half e to the power t plus x as a function of t is nothing but this whole expression c e to the power minus t plus half e to the power t. So this and this cancels. We get half e to the power t plus half e to the power t, which is nothing but e to the power t, which is equal to the right hand side. So since LHS is equal to RHS, therefore x as a function of t, which is c e to the power minus t plus half e to the power t, is the solution of the differential equation x dot t plus x as a function of t equals e to the power t. So guys, we just had to verify. We were given the function x as a function of t. We were given the differential equation. Start with the LHS, solve it, show it as equal to RHS. X dot t we get by finding out dx by dt. This is nothing but my x dot t. This is my x dot t. X of t itself, just plug in this value, solve it, you get the right hand side. Okay. Then let's solve the next question. Question 2. Consider the differential equation tx dot equals 2x. Part 1 asks us show that x, we need to show that x equals ct square is a solution of the above differential equation for all values of the constant c. And part B asks us find in particular the integral curve through the point 1, 2. Okay, so again, let's solve this question. We are given the differential equation. Let's quickly write it. Let's first solve part A. So my differential equation is px dot equal to 2x, where x dot is dx by dt. And I need to show that x equal to ct square is the solution of this differential equation. Okay, so again, let us start with the left hand side. What is left hand side? Tx dot. This is nothing but t times what is x dot? X dot is nothing but 2ct dx by dt. Okay, so x t times x dot is 2ct. This I can write as 2 times ct square. Okay, and what is ct square? It's equal to x. So 2x, which is nothing but my right hand side. So we started with the left hand side, which was px dot. I plug in the value of x dot, which is 2ct. I get 2ct square. Ct square is nothing but x, so I get 2x. 2x is nothing but my right hand side. Since LHS is equal to RHS, therefore x equal to ct square is a solution of the differential equation tx dot equals 2x. It is a solution of the differential equation tx dot equal to 2x. Okay, so hoping students have understood this. Now let's solve part B. So I am erasing this off. We need to find in particular the integral curve which passes through 1, 2. So remember, integral curve is a particular case of the solution. So our solution is, so I'm solving part B, x is equal to ct square, right? This we have shown in part A that this is a solution of, it's a general solution. This is a general solution of the differential equation tx dot equal to 2x. Now, since the above equation passes through the point 1, 2, therefore 1, 2 must satisfy the above equation. where 1 is nothing but t and 2 is nothing but x. So if I put x as 2 and t as 1, so what do I get? 2 is equal to c times 1 ka square, which implies what is my value of c I get? I get my value of c as 2. So c is equal to 2. If I plug back c equal to 2 in the equation, I get the integral curve. So x equal to 2t square is the integral curve passing through 1, 2. If all students can see, this is nothing but the equation of a parabola. This is the equation of the parabola with vertex at 0, 0. With vertex at 0, 0. Okay, so hoping students have understood this. So we were given the differential equation. We had to show that this is a solution. So we have shown that. Part B asks us that in particular, we need to find the integral curve through 1, 2. So in part 1, we have shown that x equal to ct square is a general solution. It passes through the point 1, 2. So 1, 2 should satisfy the above equation. So you put x as 2, you put t as 1, you get the value of c as 2. You plug back the value of c here. You get x equal to 2t square as the integral curve. If you go to plot this, it's going to come like this. You have t here, you have x here. You can see it's a parabola with the vertex at 0, 0. Okay, you can clearly see that x is quadratic in t. So it's a parabola with the vertical axis. You can clearly see that vertical axis is the axis of symmetry here. Okay, so moving forward now to the next question, question 3. Show that any function x as a function of t that satisfies the equation x e to the power tx equal to c is a solution of the differential equation 1 plus tx times x dot equals minus x square. Show that any function that satisfies the equation x e to the power tx equal to c is a solution of the given differential equation. Okay, so we need to show that this is a solution of this particular differential equation. Okay, so let's start. Suppose I start with the equation which is given to us, x e to the power tx equal to c. Now clearly all students can see, let me differentiate this equation, because you can clearly see that in the differential equation I have x dot, which is dx by dt. So differentiating the above equation implicitly with respect to t, I can apply the product rule here, x into e to the power tx times tx ka derivative is t times x dot plus x times t ka derivative is 1. Remember, we are differentiating with respect to t. So x into e to the power tx ka derivative with respect to t will be e to the power tx times, within tx the product rule, t times x dot plus x times t ka derivative is 1, plus e to the power tx times x ka derivative with respect to t is x dot equal to 0. So now I can take e to the power tx common. So what do we get when I take e to the power tx common? So I get x times px dot plus x dot equal to 0. Now this e to the power tx goes to the right hand side, vanishes. So this implies I get x times px dot plus x dot equal to 0. So if I further solve it, I get x times px dot plus x square plus x dot equal to 0. This implies this x square I can take to the right hand side. So I get x px dot plus x dot equals minus x square. This implies I can now take x dot common. So I get 1 plus px equals minus x square. So which is the required differential equation? Which is the required differential equation? Okay, so clearly all students can see that you started with the function which was given to us, and using implicit differentiation you have arrived at the differential equation which you had to show. Basically we had to show that this equation is a solution of this differential equation. So you started with the equation, and after implicit differentiation you have arrived at this differential equation. So I can say that this is a solution of the given differential equation. You could have also done it the other way around, guys. You could have started with, so you could have also done it like this, the way we have been doing question 1 and 2. So if I tell you the other way around, this was one method to solve. You can look at another method. Okay, you could have also done the question like this. So you could have started with the differential equation. Consider 1 plus px times x dot equals minus x square. Now our LHS is nothing but 1 plus px times x dot. Now first of all we need to find out x dot. So we are given x e to the power tx is equal to c. So if I differentiate it with respect to t, differentiating with respect to t, x times e to the power tx times px dot plus x plus e to the power tx times x dot equals 0. So I could have taken x dot common. So basically I could have got x e to the power tx times tx dot plus x square e to the power tx. I'm opening up brackets right now, plus e to the power tx times x dot equal to 0. Okay, I would have written it like this. I would have taken x dot common, so we get tx e to the power tx. Okay, then plus e to the power tx equals minus x square e to the power tx. My x dot would have been minus x square e to the power tx whole divided by, I could have taken e to the power tx common, I get 1 plus tx. This and this cancels out, which implies my x dot would have come out as minus x square upon 1 plus tx. So this x dot value which I could have got by using this method, I will substitute it here. So this becomes 1 plus tx times x dot is minus x square upon 1 plus tx. 1 plus tx cancels. I get minus x square, which is nothing but my right hand side. So I could have said that since LHS is equal to RHS, therefore x e to the power tx equal to c is the solution of the differential equation 1 plus px times x dot equal to minus x square. This is the alternative method which I could have used. Okay, so that means to solve question 3, you have two methods. You start with the equation which is given to you, you differentiate it implicitly with respect to t, and you arrive at the differential equation. Another equation is you start with the differential equation, start with the LHS of the differential equation, and prove it to be equal to the RHS. Both the methods are absolutely fine from examination point of view. Okay, so hoping students have understood this. So students, this is where I intend to stop in this particular lecture. The homework for all students who are attending this lecture is as follows. All students are requested to kindly solve this question. So the question is as follows. In each of the following cases, show that x as a function of t is a solution of corresponding differential equation. Is a solution of the corresponding differential equation x dot as a function of t and x. So I'm giving all the parts. Part A, the equation is x square plus 2 times the square root of 1 minus t square equal to 0. And my differential equation is this. This is my differential equation. Now students are requested to verify that this is a solution of this differential equation. Okay. So basically I can write it like this to make it more systematic. Basically on the left hand side you have the solution. In this case you have the function. And in this case you have the differential equation. Not actually the function, let me correct it. It's actually the solution. Or I can say that this is the curve. Now we need to show that this is a solution of this. Similarly, part B, we are given half e to the power t square plus e to the power minus x times x plus 1 plus c equal to 0, where c is a constant. Where c is a constant. Again, the differential equation is given to us x times x dot is equal to t e to the power t square plus x. Okay, this is part B. Again, we need to show that this is a solution of this differential equation. Okay, and similarly, the last part for this question, part C, we are given the equation. This is the equation. Actually, let me write it. It's the equation. So the third equation is 1 minus t times x square equals t cube. And I need to show that this equation is a solution of the equation, differential equation 2t cube times x dot equals x times x square plus 3t square. So again, I need to show that this equation is a solution of this differential equation. Okay, so this is the only homework question for all students who are attending this lecture. We need to show that all the equations given on the left hand side of your screen are solutions of the differential equation given on the right hand side of the screen. So students are going to solve these questions at home, and once you solve, you can check out the answers, because all the above questions are solved step by step in my lecture note on differential equations. You will observe that all the questions which I have given for homework, you will find step-by-step solutions to the above questions in my lecture note on differential equations. So first of all, students are requested to solve these questions on their own, and then you can cross-check the answers from my lecture note on differential equations. So students, this is where I stop. We will continue with our lectures on differential equations in the coming lectures as well. So I hope all students have enjoyed this lecture. Any doubt, you can unmute your mics and ask, or call up or mail me your doubts at divineschooloфeconomics@gmail.com. So this is where I stop in this lecture.